Hello, and welcome to Pandemic Physics. You've seen wave motion, and you know that as a wave propagates along a string, there are pieces of the string, let's say moving up and down, while the energy of the wave propagates along the string. Now, this may seem like an odd question, but when matter moves through space, for example, throwing a baseball, is it like the material of the string that's moving back and forth but somehow cut loose and just traveling on its own? Or is it a type of wave propagation like the energy on the string that moves from place to place without permanently moving the string? And the surprising answer is B, that when you throw a baseball, it actually moves through space like a wave. And some of the evidence for that would include atomic spectra, electron diffraction and interference, matter and antimatter pair production and annihilation, which shows that it's somehow equivalent with light, something called the uncertainty principle, which is a wave property of matter, and also special relativity. And today we'll just cover the first four of these. So all of these are explained by the wave model of matter. So let's start with some early theories of light, which were based on analogy with sound waves. And since sound waves need some kind of medium like the air to propagate through, it was proposed that empty space must contain some kind of a medium as well, which was called the ether, or the luminous ether. And there's an interesting history behind that, but definitely many scientists have assumed that there must be such a medium. Nowadays, people generally just refer to empty space as the vacuum to emphasize that it's not made of matter, but that doesn't mean that it has no material properties. Okay, so let's look at a little history. Back in the 1600s, Christian Huygens used birefringent crystals to separate light into two components, which are called polarizations. And you may have seen a demonstration of polarizers to show that there are indeed two different directions that the light wave can vibrate. And therefore it's a transverse wave. Also in the 1600s, Isaac Newton noted that there's a similarity between the colors of light and the tones of sound, but he criticized the wave theory because sound waves did not have two polarizations. So he thought light might consist of some kind of particles which could have different orientations. So that was his idea about light. Late 1600s, an astronomer, Olaf Romer, he deduced that it takes light about 11 minutes to travel between the sun and the Earth. And the way he did that was he was looking at the moons of Jupiter, and they seemed to slow down when the Earth was moving away, and then they would speed up when the Earth was moving toward Jupiter. And Romer realized that's because of the time it takes for the light to propagate from Jupiter to the Earth. It would be increasing as the Earth moves away and then decreasing as the Earth moves towards Jupiter. So from his data, he was able to estimate the speed of light as being about 210,000 kilometers per second. So moving a bit later, 1817, Thomas Young believed that light had to be waves because it had a characteristic speed. He suggested that light consists of transverse vibrations, such as occur in an elastic solid. So you can look in the picture here. If you start the solid shaking up and down, that vibration will propagate along the medium as a transverse wave. And of course, there's two possible directions of vibration perpendicular to the direction of propagation. So one property of light waves, or really any kind of waves, is that if you line up two different waves crest to crest, then you'll get a bigger wave. If you line up two waves peak to trough, then the waves will cancel. Okay, so this is called interference of light. And so Young realized that if you took light and shined it into two slits, that you would get a pattern of bright and dark spots depending on the difference in the path length that the light travels to the spot on the screen. So if the two paths have the same distance, or if the paths differ by an integer number of wavelengths, then the waves will add peak to peak and you just get a bigger wave. So that's the bright spots. And then in between there, if the difference in the path traveled is, let's say, half a wavelength, then the waves would add peak to trough and they would cancel. So you get a dark spot. Okay, so Young validated his hypothesis by shining light through two slits and observed an interference pattern. And here's a picture of the interference pattern, from a laser going through two slits. And you can compare that with, just the interference of water waves if you have two sources. You get the large amplitude regions and then the low amplitude regions. So even if you just have a single opening instead of two slits, you still get interference. And in fact, you could think of this as two slits that are basically touching right here in the middle. So they're separated by half of the width of the slit. So you still get an interference, and that's called diffraction in this case. And you can actually observe that diffraction if you look through two pencils that are very close together. So here's an example here. You can see the dark lines in between. So Young's ideas were used successfully by 19th century scientists to explain virtually all of the properties of light that were known at that time. Some scientists even suggested that matter itself might consist of waves. And that includes James Maxwell, who developed the electromagnetic theory, and also Sir George Gabriel Stokes, who was another prominent scientist of that time. So interference and diffraction indicate that light consists of waves. But in 1900, Max Planck explained the distribution of thermal radiation by supposing light to be emitted by vibrators whose energy could only have integer multiples of some vibration frequency multiplied by a constant. So the equation would be here that the energy had to be an integer number of some fundamental energy based on the frequency. So this type of restriction is called quantization. Okay, that you have to have an integer multiple of some quantity. Okay, and Planck's constant is given here. So we also know that light is absorbed in quantum units, which results in the graininess of low light photography. I guess it's not entirely clear if that's due to the light being a wave or due to the atomic nature of the absorber. But nonetheless, if you expose a film to light, at low levels of light, you just would get a few absorptions, so you just see a few spots. And as you get more and more light, then you build up this interference pattern for light going through two slits, for example. So measure of the probability that you absorb light in that region. Okay, and then in 1905, Albert Einstein used this idea of quantization of the radiation to explain a phenomenon called the photoelectric effect, in which it's the frequency of the light rather than the brightness that has to exceed a certain threshold in order to liberate electrons from a metal. Okay, so it turns out if you have low frequency light, then electrons are not emitted from the metal. As you increase the frequency, you start getting electrons emitted. And if you increase the frequency even more, lowering the wavelength, then you get electrons emitted even with higher energy. So in 1913, Niels Bohr used quantization of angular momentum and energy to derive the energy levels and spectral frequencies of the hydrogen atom. And in 1924, Louis de Broglie proposed that electrons have a wave-like character with the same relation between momentum and frequency as for light waves. So Bohr's idea of quantization of angular momentum became de Broglie's idea that the allowed orbits of the electron must have an integer number of wavelengths. So using his analysis, the energy difference between the nth orbit and a free electron would be this formula here. So the energy is a constant divided by the orbit number squared. So you start with n equals 1 would be the most negative energy, and as n goes to infinity, the energy would be 0. So that's measuring the energy difference from a free electron. So light is emitted when electrons move from a higher orbit to a lower orbit. And assuming that the energy of the light is proportional to frequency, using this Planck's constant relation, h times f, yields this equation that Planck's constant times the frequency is the change of energy within the atom. And that's the difference between those two energies that we just calculated before. Okay, and it turns out this spectrum of frequencies matches the observed spectrum of hydrogen. So if you look through a diffraction grating at a source of light coming from hydrogen atoms, what you'll see is this pattern of lines, and those lines are calculated from the formula that Niels Bohr and Louis de Broglie were using. Okay, and you can compare that with a rainbow, for which you would have a continuous distribution of light. So thermal radiation has a continuous spectrum like that, but radiation from individual atoms has a spectrum with just these discrete lines determined by the energy levels of the atom. So here's an example of what electron orbit might look like in a two-dimensional cut. In this case, you've got 4 wavelengths going around the orbit, which actually is more than any common atoms would have, but there it is. Okay, so that's in 2 dimensions. In 3 dimensions, the orbits look something like this. First of all, you have some atoms that they have no angular dependence of the orbit, just a radial dependence. That's what these patterns are representing. And you can think of the colors as being like colored is positive and white is negative. It's like the 2 phases of the oscillation. And so what you've got here is you have some atoms, and we're looking at the outermost electron of the atom. So you have some atoms have no angular dependence. Some atoms have 1 wavelength as you go around the circle. So it's positive to negative and back. Some atoms have 2 wavelengths going around the circle. So here you see it goes positive twice and negative twice. And then some atoms have 3 wavelengths going around the circle. Okay, and there's names for these. These are called the s orbitals, the p orbitals, the d orbitals, and the f orbitals. Those are old names from spectroscopy. Okay, so those electron orbits determine the chemistry of the atom, because those wave patterns represent the outermost electron, which is the most involved in chemistry. So the s orbitals that had no angular dependence are over here. The p orbitals that had one wavelength going around in the outermost electron, those are here. 2 wavelengths in the outer for the outer electron here, and then 3 wavelengths down here. So those electron wave patterns determine the chemistry of the atoms. Okay, and in 1927, Davison and Germer, and also Thomson and Reed, independently confirmed the wave nature of electrons by actually demonstrating diffraction of electrons by crystals. So here's a kind of reproduction of their experiment. The image on the left was made with X-rays, which are, electromagnetic waves like light. And the image on the right was made with electrons passing through the same material, which is aluminum, and having the same wavelength. So the electron energy was adjusted to have the same wavelength as these X-rays here. And you can see a very similar pattern. Okay, also in 1933, Patrick Blackett discovered these spiral tracks in a cloud chamber, which was magnetized. So the magnetic field makes opposite charges go opposite directions. So what's happening here is you have some uncharged particle coming in, which is presumed to be a photon, and it interacts with matter somehow. And the energy of the photon is transformed into the energy of 2 charged particles. So somehow the energy of a photon gets converted into an electron and an anti-electron called a positron. So that's further evidence that electromagnetic wave energy is very, very closely related to the energy of massive particles. Okay, the uncertainty principle is an interesting property of matter. If you take a wave packet and you just squeeze it down in length, then the wavelength would decrease. So there's a ratio between the length of your packet of waves and the wavelength. As you squeeze it down, you can't decrease that ratio arbitrarily, because at some point the wavelength gets smaller and smaller as well. So the Heisenberg uncertainty principle states this property a little different way. It looks at the spread of position, which would be the length of the packet, but then you multiply by that spread of wavelengths, because you don't always have a single wavelength. You have a collection of wavelengths. So if you look at the spread of position times the spread of inverse wavelengths, there's a lower limit to that. You can't make that arbitrarily small. Okay, and this inverse wavelength is actually proportional to the momentum of the wave. So what the uncertainty principle tells you is that if you know the position accurately, so you have a very small spread of position, then the momentum will be poorly known. You'll have a large spread of momentum. Okay, and actually diffraction through a slit or an opening demonstrates the uncertainty principle. So if you just have a little spot beam of light shining through a very wide opening, then you'll just see the image of that light. Let's say it's a spot from a laser. You just see a very small spot from the light. And so the vertical momentum is essentially zero. It would be all horizontal momentum. But as you squeeze the opening down, diffraction makes some of the light spread out into these bright spots, these diffraction bands. And so some of the light is getting a momentum in the vertical direction. So as you limit the size of the wave packet in the vertical direction, you generate a spread of vertical momentum. Okay, that's the uncertainty principle. And interestingly, the same thing happens for particles like electrons. So one final note is, suppose you take a string and you keep track of its orientation, like attach some bars to it. If you generate waves by, let's say, rotating part of that string, what you'll end up with is a right-handed thread on one side and a left-handed thread on the other side. So the waves that you generate in opposite directions are going to be essentially mirror image of each other. And it turns out that matter and antimatter also behave like mirror image of each other. So it's very interesting, like that cloud chamber experiment that I showed you that had the electron and the positron generated at a point. They behave like mirror image as well. Okay, so further evidence that matter consists of waves. All right, thank you for watching.